Alright, hello and welcome to another physics tutorial. So today we will be looking at problem number 37 in chapter 15, which discusses oscillations. So let's look at our question. So we have a massless spring that hangs from a ceiling, let me draw a picture over here, with a small object that is hanging at rest. So we see that our spring is at its rest length. So next, we release our spring and it starts to oscillate, with its lowest position being 10 centimeters below. So for part A, we want the frequency. So let's first take our equation for frequency, which is 1 over 2 pi times the square root of k over m. Now here's an issue. We don't know k or m and we have no way of finding them out. But something clever we can do is we can find the ratio of k over m. So here, halfway down is our equilibrium point, where mg equals kx. So we can see that mg equals kx at this point, meaning that our ratio of k over m equals g over x, which x is halfway of this 10 centimeter length, which gives us 9.8 meters per second squared over 0.505 meters, which gives us that this ratio is 196. This means that our frequency is equal to 1 over 2 pi times the square root of 196. And if you plug this into your calculator, you should get that your frequency is 2.2 hertz. Now for part B, we want the speed of this object when it is 8 centimeters below this initial position. So let's use conservation of energy. At this very top, once it's released, it has a spring potential energy of half Ka squared, where A is half this 10 centimeters from here to here. So we set this equal to half kx squared, which is the spring potential energy 8 centimeters below. And we see that because this is 8 centimeters and the equilibrium point is 5 centimeters below, our x is 3 centimeters. And our other term is half mv squared. So now let's solve for v. So we cancel our halves and subtract kx squared over, get that ka squared minus kx squared equals mv squared. Next, we divide by m and take a square root to see that v equals k over m times a squared minus x squared. I factored out this k because we have both of these. So once again, we use our ratio of k over m, so we have 196 times 0.05 squared minus 0.03 squared, and if you plug that all into your calculator, you should get that v equals 0.56 meters per second. Alright, so for part C, we attach a mass of 300 grams to the first object, and now our frequency has been halved. So frequency is 1 over 2 pi times the square root of k over m. So you'll notice that obviously we can't change 2 or pi, and k has not been changed, which means that our m has been changed. So to get half the frequency, so now we have half f equals 1 over 2 pi times the square root of k over, let's say, m prime. So we see that to get a half f, we must have that m prime equals 4m. So if our new mass is big M, so we have m plus m equals 4m, so m equals 3m. So our old mass must be 1/3 of the new mass, or 100 grams, or as I like to put it, 0.1 kilograms. So now for part D, how far below yi is the new equilibrium position with both objects attached to the spring? So once again, we use mg equals kx, where x is our equilibrium position. So we have x equals mg over k. So now we can actually find the value of k by setting, because we see k over m is 196, and we see that m is 0.1 kilograms, to get that k equals 19.6 newtons per meter. So you see that x equals mg over k, which equals, so this is our new m, which is 0.4 kilograms. So that times 9.8 meters per second squared, all over 19.6 newton per meter, to get that our new equilibrium position is 0.2 meters below yi. Okay, thank you for watching. I hope you learned something about equilibrium positions of springs in a vertical position. Please like the video, subscribe to the channel, and I will see you later. Bye!